Hello and welcome back to Maths and Science with Mrs. R. Okay, so today we're gonna be continuing with electric circuits. The difference between the series connection and the parallel connection. So I labeled them there as you can see. So the series connection is where you only have one path, as we said in the last video, and then for the parallel connection, there's more than one path for the current to flow. So the first thing to do when you look at a circuit, before you start any calculations, for you to determine if it's a series connection or a parallel connection, you need to map out your current. We need to see how your current is flowing. So as we agreed last time, so the conventional current flows from the positive terminal to the negative terminal. So we're going to map out our current for the series connection. So your current, it is the total current that is flowing here. So your total current is going to be flowing in that direction. So current yote inokotoma from the positive terminal is the total current because the current yote. So it's going to pass through A1, meaning that at A1, the reading that you're going to get is the I total, right? Then it's going to pass through the closed switch. It's not going to go to V2, V1, or V3. Why? I hope you answered. We explained it in the last video. Is because the voltmeter has a very high resistance. So meaning that it's a path that the electrons are going to ignore or to avoid, meaning that charges zacho dzingajeni apa V2, then they're gonna pass through R1, R2, A2. So the other question is, what's the reading that you're gonna get on A2? Remember, your current is flowing. We didn't hear about any place when current yashuyohera kana yo pungudzea or anything. And remember, your charges are conserved, meaning that they can't be created or destroyed. They can only be transferred. And in this case, they are not transferred anywhere. They're just going to flow throughout the circuit, meaning that the current that you're going to get at A1, it's going to be the same as the current that you're going to get at A2. Is still going to be the total current, right? Then it's going to flow back to the negative terminal, then through the battery, then back again. So that is how the charges are going to be flowing. So meaning that what we can conclude is that throughout the series connection, your current is the same. Your current is the same. And then let's go to the parallel connection. For the parallel connection, we're going to still start there at the positive terminal, headed to the negative terminal. So then your I total, the total current that you're going to start with, that's where it's going. And then meaning that at A1, you're going to get your I total. But now there's a problem here. When we get to this point, some of the charges are going to take the top path and some of them are going to take the bottom path. Zvitofanana musi ari relining. Rather, I remember the charges dzavo rine ro ndi zvisore zvavo rine zvikisvika hapa la ngauri una ndira mbiri, there's no ways une ri kho ḓo fola queue nthihi habe ya tou yo vula queue ya vhuvhili ndo wana vhathu vhaṅwe vha tshi shavha vha cheka queue ya vhuvhili, meaning that even with the charges, some of the charges are gonna go through this path right here. So let's call it I1, and then the ones that are going down here, let's call it I2, meaning that I1 ikutuwa nga hila ndira zviambori ka A2 apa ri ḓo wana I1, and then ka A3 ri ḓo wana I2. Dziki swika hapa la dziko dovha dza ita mini dza ṱangana, they still combined, and then as it goes zviamba zwori dzi tshi ḓa ngeno dzi ri kho ḓovha na mini na I total again, then dza ṱuwa nga u rala dza dovha dza vhuyelela ngei nṱha. So I always give an example ya uri, let's say for example vhana vho dzhenaho tshikoloni vhana vha total vho dzhenaho tshikoloni ndi 500, tshikoloni ho dzhena vhana vha 500, vhana vho yaho kha block ya nṱha kha hei lane ya nṱha vha vha 200, zwi amba uri vho yaho kha block ya fhasi vha ḓovha vhangana vha 300. 300 plus 200 zwi tea uri fha vhugai 500 yo dzhenaho, and then vho no ḓo bva vha ḓo tea vha vhangana vha 500. Why? Vhana vho dzhena, ahuna vhana vho xelaho, ahuna vhana vho salaho, zwi amba zwori dzi charges dzashu, current yashu yeneiḽi yo dzhenaho, as it splits, the total still needs to be the same as the one that you had in the first place, and the total at the end still needs to be the same as the one you started with. So that is how your current works. So what you can conclude from what we just saw here is that your current for a parallel connection, it will be divided. How was it divided? We saw we had I total, which split into two, which is I1 and I2. Then it was combined again to be I total again. So that is how your current flows, and that is the difference between the two. So meaning that if you find two resistors which have the same current, or which are experiencing the same current, it means that they are in series. And if they're experiencing different current, it means that they are parallel to each other. So then I want us to use FET simulations to actually see what we were talking about. So if you can see here on the top left, you have your series connection. You have two batteries there, an ammeter, an open switch there, two resistors. One is 10 ohms, the other one is also 10 ohms. I want to reduce the ohms to 5. I want us to have different ones. One should be at least 5, half of the other, then the other one is 10. Even on this one, I want us to do the same, so that when we compare them knowing that we have different resistance for the different resistors. So then here we are. So we're gonna close our circuit there, our switch there, and then when you close our switch, you need to tell me what you see. So the switch is closed. As you can see, our electrons are moving in that direction. So as our electrons are moving, or as our current is flowing, you can see that it only has one path. Then the reading on the ammeter, on this ammeter, is 1,2 amperes, and then the other one is also 1,2, meaning that the total current that you have in the beginning is the total current that you have nange magumoni. Zvibonela nga mini nga luvilo lwa dzicharge dziko gidima nga ndira yonofana, as you can see. And then now we're going to talk about the energy. We're going to connect it. So if you look at the voltmeter, how is the voltmeter connected? The voltmeter is supposed to hug your resistor, meaning that chimwe chanda chitoeva chika imwe side, chimwe chika imwe, then the resistor should be in the middle like that. So we're gonna talk about the voltages at a later stage, but let's now compare also the current flowing through the parallel connection. So with the parallel connection, so we have closed the so wait, I think I forgot to add. Let me break this here. I want to add an ammeter to it. So we know the current which went out, similar to the one which was, I think it was A4 on the other one that we drew. Yeah. Okay. Another wire to complete our circuit. Yeah, there we go. So with our two batteries there, each having 9 volts, meaning that the total here for the voltage is 18 volts. So the current there on the first ammeter is 5,5. And then when it gets here to this point, as you can see, chimwe chojena, chimwe chats, chimwe chajena, chimwe chats. I'm sorry for having that. And then the current on top here is 3,6. The current at the bottom is 1,8. As I said, your resistor is like an obstacle along the way. So the charges on the top path, they are running very fast compared to the bottom one. Why? Because the resistance on top is less than the resistance at the bottom. So right here, right now, I'm sure you are seeing the relationship which is there between the resistance and the current. So resistance, if it's big, the current is going to be small. It's 1,8. When the resistance is small, the current is going to be greater, which is 3,6. But then when they combine back here, rekaditio dova rabana 5,4 as the one that entered, because this split zatangana as they go in that direction. So I hope you understood about the current. So the next thing that I want us to talk about is the energy, which is the potential difference. So the potential difference is the voltage. So voltage yaborini. If you look at V1 here, V1 is hugging the battery. It means that the reading that you're gonna get for V1, it is the energy provided by the battery. And then if you go to R1 and R2, R1 is the energy that's going to be used up by the resistor 1, and R2 is the energy that's going to be used up by the resistor number 2. So what happens is that path in T iba yofiwa the total energy by the battery. So ka hei path ya borine ya R1 na R2. R1 na R2 ngauri dzo dzula kha path nthihi. Zwi amba zwori hedziḽa dzi charge dza borine dzi kho tea to u shumisa energy yeneiḽa nthihi. So let me explain it in this way. Let me go back to the FET simulations. So meaning that if your charges ziko takuwa phala dzina 18 volts, when they get to the first resistor, which is 5 ohms, they can't use up all the 18 volts to pass through. If they are to use up all the 18 volts to pass through, they're going to be very fast to pass through this point, but they won't be able to pass through the next obstacle. So you need energy to pass the first obstacle and the second obstacle, meaning that the energy has to be shared between the two. So if you look at this one, when we connect, it shows that only 6 volts was used up for the 5 ohms, and then the remaining 12 volts is used up to pass through the second resistor. Because remember, the very same charge which is passing through 5 ohms is the same charge that's still gonna pass through the 10 ohms ngauri dzi kha pathi yeneiḽa nthihi a huna une dza ḓo shavhela hone hune ḓo pfhi dzi ḓo dzhia shortcut, meaning that energy will be divided amongst the two resistors. You understand? So what's your conclusion now? Nduri energy data mini ido divide in the case ya musi arena the resistors in series. But then with the parallel connection, look at this. There is the charge which went through the 5 ohm didn't go through 10 ohms, meaning that the one which is going through the top part has the energy of 18 volts. The one which is going through the 10 ohms also has energy of 18 volts. You understand me? I hope you understand. Meaning that there is no division here. All the energy is going to be used up only up 5 volts. All the energy is going to be used up 10 volts, 10 ohms, sorry. Because zikapath mbili zoita umenzopamba now. So let's go and see. Let's try and connect it from up here. So the top one is 18 volts, all of the voltage nga uri helani charge inokupira nga ntha asi yone yopira nga gai nga pasi, and then also nga pasi is still 18 volts, meaning that what can we conclude when we see voltage nga hindi zviamba zvori your potential difference remember potential difference, it is the energy transferred, right? Meaning that energy is divided, and then the energy for the other two is the same. So meaning that voltage that you're gonna get for V1 for V2 is gonna be the same as the one that you get for V3. I think I showed you there, and I hope that you understand. If you still have questions, you can ask in the comment section. I will be there to answer your questions. So then at the end of the day, I like doing this table. So you can also do this table the moment you walk into your exam before you answer. So you say series and then parallel, current, and then potential difference. So how does it work? Current for series, that's the one thing that you can never forget, is the same. And then S can't have another S next to it. It's supposed to be D, which is standing for divided. The other one also D right next to it, and the other one is supposed to be S. So what are we saying? Current for series is the same. Current for parallel is divided. Potential difference for series is divided. Potential difference for parallel is the same. So that is what we know about the series and parallel connection when it comes to potential difference and current. So then now I want us to talk about the resistance. I want us to talk about the resistance. So finding the total resistance for a series connection, all you do is to say that your R total is equal to R1 plus R2. So you can add them as simple as that because zikandira nti. And then when it comes to the other one here parallel, so you have two ways. 1 over R parallel is equal to 1 over R1 plus 1 over R2. That is the formula. Or you can use the one which says R parallel is equal to the product over sum, product of the two resistors, R1 times R2 over R1 plus R2. So those are the two formulas that you can use. So in a different case, in this case, I want us to know this. For the series 1, R1 and R2 can be resistor 1 and resistor 2. However, for the parallel one, I don't want us to know R1 as resistor number 1, but I want us to know R1 as all the resistors. All the resistors on the first path. And then you're gonna have your R2 as all the resistors on the second path. What do I mean by that? Okay, so I'm gonna draw one where you're gonna have, for example, it's like that, and then path number 2, you have 2 resistors connected like that. So it means that this is R1, R2, and R3. So when you go and write in your formulas, actually you're gonna write your formula as 1 over R parallel is equal to 1 over R1 plus 1 over R2. But remember, for substitution now, R1 is all the resistors on the first path. It's only R1, right? So it's going to be 1 over R1. 1 over R parallel is equal to 1 over R1 plus the second one will be 1 over R2 plus R3, because they are both on the same path. So these ones, when you get here, if you had your I total coming through this way, I total means that this is going to be I1 and then this is going to be I2. So which resistors are experiencing I2 is R2 and R3. So what is the relationship between them? They are in series. Why? Because they're experiencing the same current. So that is how it is. That's how it is. And then now I want us to go back to FET simulations to see exactly what I mean by this. To see what I mean by this. So with the connection that you have there, we can cut it up here and then add another resistor right here. Let's move it like this. Can we reduce the resistance? Okay, so down here we have 18 because there is now 10 and 8. So now because there is 10 and 8 is now the question is, remember when we calculated the voltage which was passing through the 10 ohms, it was 18 before because 10 was sitting here alone on this path. So now let's check and see if it's still going to be the same. No, 10 ohms is experiencing 10 volts, and then the 8 ohms is experiencing, let's see, 8 volts. It's 8 volts. It's 10 volts and 8 volts. Altogether gives you 18, which is the total which is supposed to pass through this path. So it still says that because they're experiencing the same current, it means that they are in series, meaning that your charges that are passing through the 10 ohms are still going to pass through 8 ohms, meaning that they have to divide the energy that they use up throughout the entire path. I hope all this makes it easier for you to understand circuits. And from me, until next time, bye. So next time what we're going to be doing is we're going to try and find the total resistance for different circuits.